Statistics is all about randomness. So the concept that is very crucial and important, or you can say the core, is random variable. As the name suggests, random and variable. So variable means it will vary, it will take some values, it will belong to some intervals with some law or rule that is governed by this process random. So in this module we try to get a feel of the concepts of random variable. Now we'll define random variables. Is there only one definition, or we can have more than one definitions, and we will see that all the definitions are equivalent. So we'll describe or try to give an idea about all those definitions which will define a random variable. Using some simple example, just like coin toss or throwing a die, we will describe the concept of random variable. Once we define a random variable, for example x is a random variable, the obvious questions that will come across in our mind, that what will happen to any function of x, that is fx, whether fx is also a random variable. If f is any arbitrary function, will it be a random variable? If not, then what sort of condition we require so that fx is also a random variable? We'll talk about this measurable transformation. Since random variable corresponds to some random experiment, we'll describe what do you mean by random experiment, sample space, and we'll give you examples how to construct the sample space and define the random variable for that particular random experiment. We'll start the discussion with the question, what is the definition of a random variable? Because random variable is a term that we are using most of the times whenever we are talking about statistics. So it is very necessary to understand the meaning of random variable. So there are few definitions. I'll first start with the first definition. Now we'll say that x is said to be a random variable if we have this set collection of omega such that x omega less than equals to x belongs to the sigma field script f for all x belongs to real line. So this is basically a real valued function. So if for every omega this belongs to the sigma field, that is the script f, for all possible values of x belonging to the real line, then it is said to be a random variable. Now to understand this definition, we want to give one example. Suppose a coin is tossed twice. So what will be the sample space? We can have four possibilities. Both of them will be head, HH, one head, one tail, HT, one tail, one head, tail head, TH, or both of them result in tails. So it is TT. So we have four options, HH, HT, TH, TT. We define or denote this as W1, W2, W3, W4. So the W1 says about HH, W2 says about HT, W3 says about TH, and W4 says about TT. And F is the class of all subsets of omega. Now we define x omega as number of heads. So what are the possible values? Number of heads. For a coin tossed twice, we can have 0 heads. This will happen if all are tail. We can have one head. That this may happen if we have HT or TH, or at the most we can have two heads. This will happen if we have HH. So x omega will be 0 if your omega is W4, it will be 1 if omega is omega 2 or omega 3, it will be 2 if omega is equals to omega 1. Now we consider the set by the definition that for all possible values of x belonging to the real line, this set collection of omega such that x omega less than equals to x will follow script f. Now first take the condition that x is negative, x is less than 0. So we won't have any omega satisfying the condition that x omega is less than some negative value. So this set will be a null set phi, and we know phi is a set which always belongs to the sigma field script f. Now suppose x lies between 0 and 1. It can take the value 0, but it can't take the value 1. So lies between 0 closed, 1 open. Now this will happen, the set collection of omega such that x omega less than equals to x. For example, if we say x is 0, then x omega less than equals to 0 is equivalent saying collection of omega such that x omega is equals to 0, and this will happen if and only if both the trials result in tails. So it will be TT, and we know that this TT belongs to script f. Now if we just expand this limit of x as 1 to 2, so that means 1 inclusive and 2 it is not inclusive. So if x lies between 1 and 2, then this set collection of omega such that x omega less than equals to x, this will happen if and only if the sets we have consist of th, ht, tt. Now if we say x belongs to 1 and 2, so that means if the worst possible case, take x is equals to 1 and collection of omega such that x omega less than equals to 1, this will happen if we have 0 head or 1 head. So we have 3 sets contributing to this set. So th, ht, tt, and this belongs to script f. Now if x is greater than equals to 2, then we have the omega, and we know omega is a part of script f. So by definition of random variables, we can say the number of heads is a random variable. So it satisfies all the conditions that is mentioned in definition 1. Now we consider another definition. We call it as definition 2. A real valued function x defined on this omega and script f is called a random variable if x inverse b, which is a set collection of omega such that x omega belongs to b is a set, this whole set belongs to script f for all b belongs to script b, that is the Borel sigma field. So this is the definition which use the condition of Borel sigma field. So if you have a Borel sigma field and b is a member of that Borel sigma field, then we say x as a random variable if x inverse b, this set collection of omega such that x omega belongs to b belongs to the script f for all possible values of b, where b is a set belonging to the Borel sigma field. Now this is what we call second definition. Now these two definitions are not the only definitions that are available. So by saying these two definitions, or we can make some equivalent statements. X is a random variable if and only if collection of omega such that x omega greater than x, this is a set, if this set belongs to script f for all x belongs to script r, this is a real line, then also x is a random variable. If we include the equality x case, that means collection of omega such that x omega greater than equals to x, this set belongs to script f for all x belongs to r, then also it's a random variable. If we consider the set collection of omega such that x omega is less than x, and this set belongs to script f for all x belongs to the real line, then also x is a random variable. Or if we say that collection of omega such that x omega lies between a and b, where a less than equals to b, they are both finite quantity, and this set belongs to script f for all x belongs to r, then also x is a random variable. So whenever we are saying x is a random variable, we can have so many definitions, and all are equivalent definitions. Now we'll describe a few results related to random variables. Suppose x is a random variable. Then we want to see whether x square, this is a function of x, is random variable or not. Now if we use the definition 1, that we want to see the set omega such that x square omega is less than equals to x belongs to script f for all possible x. Now if we take the first condition that x is negative, x square omega less than equals to negative quantity, it is not feasible, so we don't have any such set or any collection of omega satisfying this condition, so this is a null set. Phi belongs to script f. Now if x is equals to 0, then x square omega can't be less than 0, so it must be 0. So it will be 0 if and only if x omega is equals to 0. and x is a random variable. We have assumed that, so this belongs to script f. Now if x is positive, then x square omega less than equals to x implies x omega lies between minus square root of x to plus square root of x, and x is a random variable, so once again this set belongs to script f, so x square is a random variable. Now this is one particular case we are talking about, but any continuous function of x is a random variable. Now what do you mean by continuous function? So the definition of a continuous function is such that for every epsilon greater than 0 there is a delta which is positive, such that whenever the absolute difference between fx and fx minus fx0 is less than epsilon, whenever x minus x0 is less than delta. So it says that whenever the difference between the arguments is less than some delta, the difference between the functional value will be less than epsilon. And if this condition is satisfied for a particular function, that function is said to be a continuous function. So any continuous function of x is a random variable. Now we consider special cases. That we have two random variables y and z. Now we want to see whether y plus z is also a random variable. Now note that y plus z greater than x, these two random variables take the sum is greater than x if and only if there is a rational number q in the interval such that y is greater than q is greater than x minus z, so that y is greater than q and z is greater than x minus q. That is what we want to say, that y plus z is greater than x is, this set is equivalent by saying considering union over all possible q's such that y is greater than q and z is greater than x minus q. If these two conditions are simultaneously satisfied, then we will have this result that y plus z is greater than x. So y greater than q or z greater than x minus q, we know their y and z are their random variable, so y plus z is also a random variable. What about a random, what will happen if a random variable is multiplied by a constant? Now assume that c is greater than 0, so we want to see whether cy is a random variable or not. It is, because cy less than x is nothing but y is less than x by c, and we know that y is a random variable. What will happen to the product y into z? Now we can say yz can be written as half of y plus z whole square minus y square minus z square. We know that if y plus z is a random variable, its whole square is also a random variable. So the first quantity is a random variable, second quantity is also a random variable, third quantity is also a random variable, and I am taking a linear combination of this random variable, it will be a random variable for sure. Now what about maximum of yz? It can be written, the maximum of yz can be written as half of modulus y minus z plus y plus z. This is all this quantity, they are random variables. Minimum of yz, once again we can write it in this way, y minus mod of y minus z minus y plus z, and this minimum is also a random variable. Now if we take only the positive part of the random variable as x plus, which is maximum of x and 0, it is also a random variable. X minus, which is the minus of minimum of x0, is also a random variables. So all these 7 cases are all random variables. This is not exhaustive list, we are giving some special cases we are mentioning. Now we consider a sequence of random variables. Let xn be a sequence of random variables. Then if we define infimum, then infimum of xn is also a random variable. Liminf, limit of this infimum, is also a random variable. Supremum of xn is a random variable, and limsup is also a random variable. To prove that infimum of xn is a random variable, we can see in this way that infimum of xn is greater than equals to x. That means is nothing but intersecting n from 1 to infinity, xn greater than equals to x. Similarly, lim of inf xn greater than equals to x, that is equivalent by saying xn is greater than x minus 1 over n for all but finite number of cases, and for all m belongs to 1, 2, 3 and so forth. So if we can prove this for infimum of xn and lim_inf of xn, just replacing xn by minus xn, we can get the similar result for supremum of xn and lim_sup of xn. Now one very interesting topic is that if we transform the random variable, we talk about measurable transformation, then whether that transformation result in a random variable or not. So let x be a random variable defined on this script. Omega is the sample space, script f is the sigma field, and p is the probability measure, and we are defining a function which mapping from real line to real line be a function. Now the question is that is fx a random variable? Well, to understand that, we just follow the figure we have written here. So for omega, from omega we have x omega which maps from omega to real line. Then for this x omega, from here we are mapping f x omega, which once again from R to R. So this is sort of convolution between f and x. F is a function as well as x is a function, both are real valued function. So this is the thing we are interested to know whether fx is a random variable or not. If f is arbitrary, fx may not be a random variable. Then when fx is a random variable? If f is Borel measurable, that means the pre-images of Borel sets under f are also Borel sets, then only then this is random variable. Now if you see the figure once again, if we have such inverse mapping, then we call this as pre-image of Borel sets, then this is a random variable. It is clear that the pre-images of Borel sets on the composite function fx are events. Then fx is a random variable. And we can extend this concept from univariate to multivariate setup. Suppose we have, instead of one random variables, we have a vector x1, x2, xn, then fx1, x2, xn is also a random variable under this condition that they are Borel measurable functions. And here in the multivariate setup, it's mapping from Rn, that is the n-dimensional real line, to real line. Now we are talking about random variable, so this has high correspondence to the random experiment. So what do you mean by a random experiment? A random experiment is a process characterized by the following properties. First of all, it is performed according to some set of rules. It can't be performed arbitrarily. It can be repeated arbitrarily often, and the result of each performance depends on chance and cannot be predicted uniquely. We can easily find few examples. Tossing of a coin. The outcome of a trial can be either head or tail showing up, so we don't know which one will come whenever we are tossing a coin. Whenever we are throwing a die, we don't know which one will come, but we know that either 1 or 2 or 3 or 4 or 5 or 6 that will come. We can have sequential random experiments performing a sequence of simple random sub-experiments. First toss a coin, then throw a dice. This is sequential. Sometimes the second sub-experiment depends on the outcome of the first. Throw a dice first if it is even, then toss a coin. So it depends on the previous outcome. And a random experiment may involve a continuum of measurements. Say the height of a student takes some value between 165 cm to 170 cm. Now whatever may be the random experiment, corresponding to the random experiment we will have a sample space. Sample space omega of a random experiment is defined as a set of all possible outcomes. These outcomes are mutually exclusive in the sense that they cannot occur simultaneously. And a sample space can be finite, countably infinite, or uncountably finite. Take this example, toss a coin 2 times. Then the sample space omega 1 will be HH, HT, TH or TT. This is countable and this is called discrete sample space. And we define B as H and T, then omega 1 is B into B. So toss a dice until a 6 appears and count the number of times the dice was tossed. So it may be 1, it may be 2, it may be 3. So this omega 2 is discrete and countably infinite. 1 to 1 corresponds with the positive integers. That's why we are saying that it's countably infinite. Now if we take another example, that pick a number x at random between 0 and 1, then pick a number y at random between 0 and x. So this set omega 3 is collection of x and y such that 0 less than equals to y less than equals to x less than equals to 1 is a continuous sample space. So the sample space can be discrete, can be continuous. It can be finite, it can be countably infinite, or it can be uncountable too. Now we have this coin example. Suppose a coin is tossed twice. So the omega, we know that it's HH, HT, TH, TT, and the sigma field we are considering is sigma x, and x omega is the number of heads. It can be 0, it can be 1, it can be 2. So x omega will be 0 if TT appears, it will be 1 if HT or TH, or it can be 2 if HH occurs. So if you see it in a figure, so HH corresponds to 2, HT or TH corresponds to 1, and TT corresponds to 0. So what this random variable is doing, it's mapping from the sample space to the real line. Here it is taking only 3 values, 0, 1 and 2. In this module we have learned the definition of random variable. We have given so many examples for a random variable. If x is a random variable, what sort of functions will be a random variable, what will happen with the sequence of a random variable, whether lim sup or liminf or any other sort of function of xn are measurable or not, that is random variable or not. So we have defined all these cases. Then we define measurable transformation. That means what sort of functions will also be a random variable. So if x is a random variable and f is a Borel measurable function, then we define that, or we've proved that fx is also a random variable. Then we define sample space of a random experiment, and on the basis of this random experiment we define the random variable. So this is a notion we require to know very clearly to understand the meaning of random variable if we want to understand statistics. So this is just a beginning, and I hope this module will help us to understand the concept of random variable.